Hi everyone, I hope that you're all doing great. So I am Lina, a third year student at the Higher National School of Computer Science. Welcome among us today in our second DevFest conferences session. So basically DevFest is a short for Developer Festival. It is an annual technical event organized by Google Developers Group. It delivers conferences and workshops to students, developers, professionals, and tech enthusiasts in general. So today we'll be having two interesting talks, and I will let you know with Usama.
Hi, this is Usama Atiyah Abdurraouf, and I am a second year student at the Higher National School of Computer Science in Easy Algiers. Well, today and once again we are here with our great speaker and our great data scientist Nazim Bendib. Well, Nazim Bendib is a fourth year student at the Higher National School of Computer Science Easy Algiers. He is also an NVIDIA Deep Learning certified instructor and a data science teacher and content creator at Codelabs Academy. He is here with us today, 25th November of 2022, to deliver a very, very great and an excellent speak about the supervised learning. Self-supervised learning. Well, I'm gonna let you with Nazim Bendib.
All right, thank you, Osama. Hello, guys. I'm going to briefly present myself. So my name is Bendib Nazim. I'm a fourth-year student at Easy Algiers. I'm a data science student. I'm also an NVIDIA DLI, so I'm a deep learning instructor. And I work at Codelabs Academy, so I'm both a content creator, a data science content creator, and I'm also a teacher. I also write some blogs on Medium, etc., mainly scientific blogs. So yeah, without further ado, we are going to talk about learning, which is quite interesting, I guess. Brandon, I'm going to talk about supervised learning for now. So just a quick recap. Supervised learning is just a training paradigm in AI in which we train a model on labeled data. So a labeled data is just a data set composed of pairs of inputs and outputs. So we take the inputs, we pass them through the model, and then the model is going to predict something, to predict like an output. We are going to compare this output to the actual output, which are the labels. And then if the output and the prediction are pretty close, we're fine. Otherwise, we need to upgrade our model so that in the next time, the output of the model is going to be much, much closer to the actual labels. And yeah, supervised learning is quite like it's the most famous paradigm in AI. Many applications are built using supervised learning, like classification, generation, etc. But it really seems like so because if we want to go to the next level of AI, if you want to create AGIs and superhuman performance machines, supervised learning can be a little bit limited. So it seems like it's not the best way to do things. All right, and I'm just going to show you why. So like as a researcher, we try to compare machines to humans, right? So we take a human, we try to define his characteristics, and then we try to implement them mathematically on an AI model. So let's just compare humans with machines. If we take a newborn or just a 1 year old or 2 years old baby, and we show him a few pictures of a cat, this baby is going to be able to recognize any cat he sees, all right? We show him 5 pictures, and then eventually he's going to recognize all the cats. But on the other hand, if you take an AI classifier or an AI system, in order to train it, you need to pass like thousands and thousands of cat images, all right? And we can clearly see the difference. A human takes few images to learn, but the AI system takes much more than that. Another example is driving cars, all right? So as a human, it only takes us for about 20 hours of training in order to drive a car correctly, all right? But on the other hand, our best reinforcement learning systems, they take thousands and thousands of hours in order to learn how to drive a car, all right? And they are far away from being as performant as a human. So there must be a problem in there. And what's really special about us as humans is that we don't really need interactions to learn things because we can learn things just by observations. So if you compare this to an AI system, and AI systems need to interact with things. And if I say interaction, I don't really mean it in the sense of touching physical things. Interaction means being exposed to many, many examples. All right? So this is a diagram that shows the progression of the human tasks, especially in the very first months of the baby. So as you can see here, we have the x-axis, which is the age of the baby with months. And here we have like the tasks that this baby learns. So you can see that in the very first month, a baby can learn face tracking because a baby can look at his mom and he can track her face, all right? And this is actually a really hard task because in machine learning, to do face tracking, you need to first do object detection. Well, before that, you need to do object classification and then object detection, and you need to track, all right? And this is actually really hard, but a baby can do this in the very first month. If you go to the third month, the baby can learn about the object's permanence. It means that the baby now knows that an object does not just appear and disappear suddenly, all right? Objects are permanent. He's going to learn eventually about the stability and support. He's going to learn about the gravity of things, all right? So if he holds an object and drop it, he knows that the object is going to fall down and not up, all right? And he's going to learn also about the sources of events. So any light or any sound or touch has a source and cannot just come from nothing, all right? And what's really, really interesting about this is that in the very first months, the baby cannot interact with anything because he cannot move. He's just laying down and observing the world. So all these very first tasks are learned by observation and not interaction. And this is something that our best AI models cannot do, all right? What we want our AI models to do is that we want them to learn just by observations. We want them to learn about the model of the world, about gravity and permanence of objects, etc. That was one problem of supervised learning, because with supervised learning, we can do this. A second problem is that nowadays, we notice that the bigger the model is, the more performant it is, all right? If you go back to 2015, maybe our biggest model was just 60 million parameters. It was the Microsoft ResNet. 1 year later, we had the Baidu Deep Speech with 300 million parameters. We had, in 2017, the Google Neural Machine Translation with 8 billion parameters. And then we had the Google T5 with 11 billion, GPT-3, which is pretty famous, with 175 billions. And in 2021, we had the Megatron Turing NLG with 530 billion. So this was just a collaboration between Microsoft and NVIDIA, and they came up with this huge natural language model. And as you can see, the sizes of the model are exponentially growing, all right? And we're doing this because we noticed that if you take a model, you scale it up, and you train it again, you're going to have much better performances. Just take a look at the GPT family. GPT-3 is bigger than GPT-2 and much more performant. GPT-2 is also bigger than GPT-1 and much more performant, etc. So this rule really stands. But the thing here is that if you take a big model and you want to train it, you need to take a big data set, all right? Otherwise, your model is going to hugely overfit on the small data sets. And since we're talking about supervised learning, we need to collect labeled data. Here we can see that there is a logarithmic relationship between the data set size and the performance, all right? So basically, if you increase your data set size exponentially, you are going to linearly increase the performance of your model. And we can see this pattern in all of the tasks in here. We have image classification, audio classification, text classification, etc. And we can see that if we exponentially increase the data set, we are going to have this linear pattern. And it's really beautiful because even though we are using like different modalities, different tasks, we can always find this pattern in here. It means that we are correct, all right? But the thing here is that if you want to have more labeled data, it's going to cost you a lot. Like it's going to cost you in terms of time because it's going to take a lot of time to label things. For example, you go to the the videos of YouTube and you want to label them, it's going to take you an eternity to do that. It's practically impossible. And the second thing is it's because it's going to cost you a lot of money, all right? Because in order to label data, you need to bring out experts, and these experts are going to label the things, and you're going to pay them, which is not practical also, all right? We want to do everything for free. What's really interesting here is that I like labeled data, we have a huge amount of unlabeled data just out there in the internet, all right? For example, we have all of Wikipedia, we have all of Reddit, all of Twitter, all of the websites in the world. They contain textual data, which is unexploited, all right? You can see here the different sizes of data sets. So in millions, so if you take this, which is pretty much the smallest one, we have here 1,000 million word, which is pretty huge, all right? In the other diagram, we have the number of videos. If you check the YouTube 8M dataset, you have for about 10 million videos, all right? And these videos are not labeled. And it would be super great if you can just exploit this. What if we train our models on this huge amount of unlabeled data? It's going to be magical, all right? And this is actually where the self-supervised learning intervenes, all right? With self-supervised learning, we can train our models on unlabeled data, but with the use of supervised methods. So what we're doing here is basically come up with an unlabeled data, and then we will formulate our problems. We will create some loss functions, some paradigms, in a way that we are going to automatically generate labels from the unlabeled data itself. So it sounds ironic, but it's pretty intuitive. So if you take a look at the SSL in natural language processing, so self-supervised learning in natural language processing, let's suppose that I only have this sentence, which is my only data set, all right? The cat was running after the mouse. It's clearly an unlabeled data because I only have one sentence. I don't have any targets, any labels, etc. What I'm going to do is I'm going to do autoregressive modeling, which is a pretty famous task in machine learning. It means that I want to create a model that, given sentence, it's going to predict the next word of the sentence, all right? So from this sentence alone, I can come up with many pairs of inputs and outputs. So for example, I can have the cat was as inputs, and I can have running as a target because the cat was running. A second pair, I can have the cat was running after, and as a target, I can use the, because the cat was running after the mouse. All right, so from an unlabeled data, I could come up with some labeled data. And this is just one formulation. What I can also do is that I can take a sentence, mask out some words, I can just delete them, and I want to train a model to just recover these sentences. This is called a mask language modeling, which is a second formulation for SSL in NLP. They can have just a bunch of that. But today we are going to focus on something called visual representation learning, which is the self-supervised learning side in computer vision. If I try to do the same with videos, well, it's pretty intuitive. So instead of taking a sentence and predicting the next word, what if I take a video and I predict the next frames of the video, all right? So it sounds pretty logical. I take a video, I mask out the future frames, I only give the past frames to the model, and then the model is going to generate the future frames. I can do it backward, so I can give the model the future frames, and this model is going to just predict or generate the past frames. What I can also do is that I can take the whole video, mask out like a few hundred frames in the middle, and I would tell the model, please recover this part of the video, all right? So yeah, it seems pretty logical. The thing that, unfortunately, it does not work as good as in NLP. Basically, it does not work at all because computer vision is much, much harder than NLP. In autoregressive modeling in NLP, what we're trying to do is that, given sentence, I want to predict one word. And this word is going to be chosen from a vocabulary. A vocabulary size at max is going to be 100 million words, all right? So what my model is going to do is that it's going to map a distribution over all these words, and then I'm going to sample from this distribution. So a distribution over these discrete words is pretty easy and doable. And this is what we've been doing all this time. But in computer vision, if I try to do this, for example, I want to predict one frame. A frame, let's assume that it's 100 by 100, all right? It means that this frame contains 10,000 pixels. That's already a lot. And let's assume that I have values between 0 and 255. So I need to do 256 times 10,000. That's pretty huge. And this is just in the case of grayscale. If I'm using RGB images, it means that I'm going to multiply the whole thing by 3 because I have 3 channels: the blue, the green, and and RGB, and the red. All right. And this is just the case for one frame. Imagine if I want to predict 100 frames. It means that I'm going to multiply the whole thing by 100, which is so extremely huge, and it's not practical at all to just map a distribution over all the possibilities. We call it the set of possible frames. It's practically impossible. So we are just dropping out this idea. We can't do autoregressive modeling in computer vision. We need to come up with something that is better. So the thing here is that we can see self-supervised learning from another perspective. There is something called energy-based models. So an energy-based model is quite similar to a simple model, but here's the thing in here. This model is going to take two inputs. It's going to take x as an input and y as an input. And it's going to predict one real value. It's just one scalar, all right? This scalar is called an energy. So if x and y are pretty compatible with each other, the energy is going to be low. And if x and y are incompatible with each other, the energy is going to be pretty high. And this concept is inspired from physics. So in order to train such an energy-based model, what we are going to do is that we are going to pick x and y that are compatible. We call them the positive pairs because it's a pair of two inputs that are compatible. We pass it to the model and we train it in such a way that it's going to produce a low energy. On the other hand, I can come up with negative pairs, which means that I'm going to come up with x's and y's that are incompatible with each other, pass them through the model, and I'm going to train it in such a way that it's going to maximize the energy. All right? The first part of the training is quite easy because it's quite simple to come up with. Positive pairs. All right? But the thing is that how can I come with negative pairs? It seems pretty easy. For example, let's consider the case of videos. All right? Like in here. What I can do is that I can bring out 10 frames as x and 10 other frames as y and pass them to the model. So if the frames of x and the frames of y are from the same video, the model is supposed to generate a low energy because these two sets of frames are pretty compatible. They are from the same video. But on the other hand, if I bring out frames that are from one video and other frames from another video, I'm going to have a high energy. The thing is that how can I choose the best negative pairs to pass to the model? Because there is actually an infinity of negative pairs, and I can't just pass them all to the model. I need to perfectly choose the best negative pairs in such a way that I'm going to maximize the training of my model. And this task is actually really, really hard. So what we are going to see now is one of the best methods that has been created by researchers in order to do such thing, to create such an energy-based models. The first one is called SimClear, which appeared in the paper Simple Framework for Contrastive Learning of Visual Representations. It's pretty famous. So basically, this is the architecture of the whole training procedure. What we are going to do is that, well, first I'm going to use two models. I'm going to use an encoder model F, which is basically just a CNN, like multiple CNNs stacked on top of each other. It's just a feature extractor, all right? It takes an image as an input and it predicts a feature vector, or at least a feature map. And I also have a projection hat. So projection hat is no more than a simple multi-layer perceptron. So two forward layers stacked on top of each other with, well, three layers stacked on top of each other with one hidden layer inside. And I'm going to use RealU, for example. So I'm going to take X, which is an image. I'm no longer working with videos. We're just considering images for now. So I come up with an image from my dataset, and I'm going to generate two new images from this very image. So I'm going to use data augmentations. All right. So I think you're pretty familiar with data augmentations. A data augmentation means taking an image and applying some distortion on the image. All right. For example, I can play with the contrast of the image. I can change it. I can play with the brightness. I can do some color distortions like hue. I can rotate the image. I can zoom in or zoom out. I can flip. I can switch the channels, put the red channel inside of the green channel and vice versa. So I can do like a whole bunch of stuff in order to change an image. All right. So I'm going to use two transformations of this image. So for example, I'm going to take the image, I'm going to distort it a little bit, and I'm going to take the same image and I'm going to take some crops, some grayscale crops, for example. So it's the same image, but with different styles. Then I'm going to pass both images to the encoder model. The encoder is going to output what we call representations, because it's a representative vector of this image. And then these representations are going to be passed through the projection head model, which is G in this case. So the goal of the projection head is to map the representation vector into a smaller dimensional space, all right? And the loss function is going to be applied upon this small dimensional space. So Hi and Hj are the representations, and Zi and Zj is the projections, all right? What I'm going to do here is that I want to maximize the distance between the projections if I'm using negative pairs, but in the case of positive pairs, I want to minimize the distance between the projections, all right? So the loss function is going to be as follows. It's pretty similar to a softmax. It's slightly different. So the loss function is applied only on positive pairs. I don't need to apply it on negative pairs. So what I do is that I take the projections of a positive pair, calculate what I call a similarity, use a similarity function. For example, cosine is the most used one. So I calculate the similarity, divide it by the temperature, and then just raise it like to the exponential and normalize it over the sums of all the exponentials. And this is going to be the loss of my positive pair. And to calculate like the whole loss, I'm just going to add all the losses of all the positive pairs and just normalize them with 2n. And yeah, it works pretty good. Like we can reach some accuracies of 60% in a classification task without any labeled data. Like, can you imagine this? I just bring out images, like millions of images. I'm going to train my model on these images without labels, and then this model is going to perform really good compared to a model without labels. So what's really interesting about this paper is that they study the effect of many data augmentations. They came up with the best combination. So before doing this, maybe we should talk about how do we evaluate such methods, all right? So when I train a model using self-supervised learning, I'm going to train it in such a way that this model is going to output some really good representation, because this is the goal. The goal is to come up with a model that represents at best all the images. So once I do this, I'm going to just come up with an SVM, for example, and I try to train it upon these representations in order to do a classification task, for example, all right? So I'm going to take all the embeddings, all the representations that has been outputted with my SSL model and use them in an SVM with an SVM classifier. So all the values that you can see here are just the accuracies of the SVM training, all right? And as you can see here, we use many combinations of transformations. We have the cropping, we have the cutout, we have the color distortion, sobble, noise, blur, and rotate. And we can see that the best combination that gives me the best accuracy is the combination between the color distortion and the cropping. It gives us an accuracy of 55.8%. All right. On the other hand, I can have some really bad accuracies by using other combinations. For example, sobble with the blur, it gives me just 6% accuracy. Sobble with sobble is just 4% accuracy. All right. The diagonal here means that I'm not using combinations. I'm just using one data augmentation at a time. All right. So if I only use cropping, it gives me 33% accuracy. If I only use noise, it gives me 9.8% accuracy, etc. So as you can see here, the best combination is between the color distortion and the cropping. And yeah, actually, we do have two types of data augmentation. We have the spatial geometric transformations, which are the data augmentations that plays with dimensionality of the image. Maybe we can do some cropping, zoom in, zoom out, etc. And we have the appearance transformation. Here we play with the appearance of the image, actually. So we can change colors, we can change channels, raise it to the blue scale, use some noise, some blur, etc. And in this paper, they said that a combination of the two is the best. Another paper came up right after. It's called SimClear, which stands for Simple Siamese, from the paper Exploring Simple Siamese Representation Learning. So in this paper, it's a little bit different, all right? So I'll be using an encoder model. So here we have an encoder model, and I have my prediction MLP, which is exactly this as the same way. But here, what I'm going to do is that I'm going to take the embedding of the first image, and I'm going to make it as close as possible to the projection of the second image. And I'm going to do the opposite. I'm going to take the embedding of the second image and make it as close as possible to the projection of the first image. This is a pseudocode in here. It's so clear. So X is my image. I do two augmentations to have X1 and X2. X1 and X2 are passed to F, which is my encoder. I get Z1 and Z2, which are the representations. Z1 and Z2 are passed through H, which is the projection layer. All right, or let's call it the prediction layer for now. It gives me P1 and P2. And then I'm going to calculate the loss, which is basically the similarity between P1 and Z2 and P2 and Z1. And then I'm just going to backpropagate and update my model. The thing here is that we need to use stop gradient. So by using stop gradient, like here, it means that the predictions Z1 and Z2 are going to be considered as constants and not just as variables from the model. It means that when I do backpropagation, I won't let any gradient flow from Z2 and Z1. I'm just going to let the gradient flow from P1 and P2, all right? Otherwise, my model is going to collapse. It means that my model is going to output some really, really bad representations, or more likely, it's going to output the same representation every time, which is quite bad, all right? So the stop gradient is actually a critical setup in order to make it work. Finally, we have the Barlow Twins, which is one of my favorite, actually. It was created by Meta AI, which is an AI research team of Meta, Facebook. So they noticed that the representations from the previous methods are quite redundant. What do we mean by this? As I said earlier, the representation must be as rich as possible, all right? It must contain as much information as possible. Otherwise, it's pretty bad. So they noticed that some of the dimensions of the embedding vector are quite redundant. So if you take, for example, an embedding of 10 dimensions and you calculate the cross correlation between two dimensions, we are going to see that it's pretty high. It means that there is an information redundancy in here. And it's quite bad. We don't want this. We want that each dimension contains as many unique information as possible, all right? So they made sure to train the model in order to do this. So basically, they come up with a batch of images. We create distorted images using data augmentation, exactly as in SimClear and Simpson. We pass them through the model in here so that we get our embeddings exactly in the same way. But now we are going to use a brand new loss function. So what we are going to do is that we are going to calculate the cross correlation between the embeddings of A and the embeddings of B, all right? Which gives us a square matrix like this. The goal is to make this square matrix as close as possible to the identity matrix. Wow, why do we need to do this? So if I formulate the loss function like in a quite different way, it means that I want the diagonal elements to be as close to 1, which are right here, and I want all the other elements to be as close as 0 as possible, all right? So we will have two terms in the loss function. We have the invariance term and the redundancy reduction term. So this first term will make sure that the embeddings of the augmentations of the same image is going to be the same, all right? So if I take positive pairs, calculate the embeddings are going to be as close as possible. And this is our first goal. The second goal is to reduce the redundancy in my embeddings. And I'm going to do this by minimizing the cross correlation between all the embeddings, all the dimensions of the embeddings, all right? And that's why I want it to be as close to 0 as possible. So by using the loss function, I'm going to make this happen, all right? I'm going to make the embeddings of the positive pairs as close as possible, and I'm going to make the dimensions as unique as possible so that the cross correlation between different dimensions is as close as possible to 0. So yeah, this is actually how we calculate the cross correlation. So basically we take Z1 and Z2, which are the outputs of my models. And then we have B1, B2, B3, and B4. So these are the number of samples. And we have the dimensions in here. So here we have three dimensions per embedding. All right. To calculate the cross correlation, all we have to do is to take the embedding, to take the dimensions one by one, and to just do some dot product, all right? And then we will have our cross correlation matrix. And I want to make this as close as possible to the identity matrix. And here are some of the best results of these self-supervised learning models. As you can see here, with just unlabeled data without any labeling, we can reach an accuracy of 80% in the top one score, and you can reach an accuracy of for about 96% in the case of the top 5 accuracy. All right, which is pretty similar to training models with labeled data. Now you choose. Do you want to train a model with labeled data, which is pretty expensive in terms of time and money, or would you like to train your models on unlabeled data, which is free for everyone? All right. So basically, that's it. Thank you for listening to this talk. I hope you enjoyed it. I'm open to questions. So yeah, I think we have 15 minutes for questions. You can ask whatever you want.
Thank you so much, Nazim Bendib, for this amazing and outstanding talk. So feel free, if you have any question, feel free to ask. Well, can we start with the questions? There are like 2 in the chat.
All right.
Yeah, so someone said Gizuri Ziyad. Well, he was asking about the bottomnet, and then Nasolakas, he was like, "Hello, sir. How to use independent component analysis (ICA) to pre-process images?"
Well, actually, the thing about self-supervised learning here is that we don't need to pre-process images at all. All right, we just come up with the images, and we are going to apply data augmentations upon them. There is no pre-processing. So we take the image, we apply color distortions, cropping, etc. We pass them to the model, and then we try to maximize and minimize the distances. So there is actually no use of pre-processing in here. All right.
Yeah. Do we have another question? So as I said, if you have any question, feel free to ask. Your question will be taken into consideration. Kazuri Ziyad said, could you provide us with resources to learn, please?
All right. Concerning, do you want resources about just some basic deep learning or about self-supervised learning? Because I can send you some research papers about what you've seen just now. All right. All right, for the basic stuff, maybe you should start out with. All right, I think Kaggle is a pretty good start. You can start out with Kaggle. So I think you know about Kaggle. It's a platform in which you can find some pretty basic tutorials for beginners. You can find some competitions in which you can compete, learn from each other, etc. So yeah, that's pretty useful. You can learn from. Well, in deep learning, we have 2 main frameworks. We have TensorFlow and PyTorch. So you can go to their official website. You can find some, you can find some pretty good tutorials in there, some pretty good notebooks. So yeah, just pick out a framework. I prefer PyTorch, and start doing some projects with it. All right, that's the best way. That's the best way to learn. Otherwise, if you want blocks, etc., it's going to be extremely hard. So for a beginner, I suggest that you just start with projects. All right, and then you dive deeper into deep learning. There's a lot of math and probability that you won't handle. You probably won't handle in the beginning.
Well, Nazim, I think I have a question myself.
Right.
I have a question.
Go ahead, yeah.
So I've seen you talking about the accuracy or the results or self-supervised learning. My question is, why considering self-supervised learning over simple modeling or simple?
All right, yeah, good question. So if if you work with supervised learning, you would need labeled data, all right? It's clear. And to get labeled data, it's pretty expensive, all right? You need to hire experts to label it. It's going to take a lot of time. Let's, for example, consider the videos of YouTube. Do you think we can label all the videos of YouTube? It's practically impossible. But we would still exploit them, all right? I would love to exploit all the videos of YouTube, right? So supervised learning won't let me exploit YouTube videos. But self-supervised learning can formulate all the problems in such a way that I'm going to use YouTube videos in order to train my model. The same thing goes for textual data. I can come up with all of Wikipedia and train my model. The Wikipedia data is not labeled at all. It's just a bunch of text, right? So yeah, with the use of self-supervised learning, I can come up with all this amount of data and train my model. That's why I prefer, most of us should prefer self-supervised learning over simple supervised learning, all right?
Yeah. There is another question which says, what do you think about using reinforcement learning in classification?
So yeah, we have another question in here. What do you think about using reinforcement learning in classification? All right. I don't recall talking about reinforcement learning in this talk, but yeah. So classification can just be solved using supervised learning, all right? You can just use supervised learning, break out, for example, cats versus dogs. We have thousands of cats images, thousands of dog images. We can do it straightforward. And I think it's better to do it that way, all right? Otherwise, if you would like to train a reinforcement learning model to do a classification, first of all, I don't see why would you do that? Because actually classification is a solved problem, all right? CNN can do that. And even though you are going to use reinforcement learning, you are probably going to use CNNs, all right? So you're kind of coming back to the same solution. But the thing, I think what's better about reinforcement learning here is that your agent is going to explore many paths in order to do the classification, all right? And that's actually really good because your agent here is going to kind of learn some unique representations, all right, that has not been learned with simple CNNs, okay? But to be honest with you, I don't see the point of using reinforcement learning. Maybe you would like to clear out your idea, all right?
Yeah. Yeah, so Nasr said, thank you, you are amazing.
All right, thank you, Mr.
Is there any other question? Well, I think there are no other questions. Yeah, so thank you so much, Nazim Bendib, for this outstanding talk. We are so pleased to have you here and today.
All the pleasure is mine.
Yeah, so anything to add, Nazim?
Well, thank you, GDG, for organizing such an event. DevFest is, I think, one of the best events in Algeria, to be honest with you. So yeah, there will be a hackathon, there will be challenges, so you should get excited about this, actually. And thank you for organizing such an event. And thank you for inviting me to do this talk. I was really happy to do this. And yeah, thank you.
Yeah, the pleasure is mine. But Nazim, please, we still have the last question, which says how self-supervised learning labels its examples. I think that this is the last question.
I think there's another question in here. So how self-supervised learning labels its examples? So yeah, for example, in the NLP, I just showed you an example. So I'm just going to re-explain it, I think. So if you take sentence, for example, I am happy, all right? It's just a simple sentence. There is no label in it. It's just one unlabeled sentence, all right? In self-supervised learning, I can extract some labeled pairs. So for example, in the task of masked language modeling, I take the sentence, I mask out some words, and then I train the model to fill out in the gap, kind of, all right? So for example, from this very easy sample, I am happy, I can mask out the word am. So it becomes I void happy. And the target is going to be I am happy, all right? So here I have a pair of input outputs. The input is I mask happy, and the output is I am happy. This is actually a labeled pair, all right? Now I can use my model, I can train it upon this labeled data, etc. So this is one formulation, all right? We can find like a whole number of formulations. Another example, I can take the input, I can change the order of the words. So for example, I am happy, it becomes happy am I, or happy I am. Yeah, it sounds bad, all right? So I can train model in order to reorder these sentences. So here I have a new pair. The input is happy I am, and the output should be I am happy. So this is input output. This is actually a labeled pair, right? So this is another formulation. In NLP, we can find a lot of formulations in order to transform unlabeled, unsupervised problems into supervised problems, so that we can train our models on unlabeled data.
Yeah. So thank you so much, Nazim Bendib, for this outstanding talk. Well, I'm just wow. So yeah, well, dear audience, I'll see you on the other talks. Thank you so much for joining us. Stay tuned for the etc. Thank you.